In mathematics, specifically, in topology, a surface is a two-dimensional, topological manifold. The most familiar examples are those that arise as the boundaries of solid objects in ordinary three-dimensional Euclidean space R3, such as a sphere. On the other hand, there are surfaces, such as the Klein bottle, that cannot be embedded in three-dimensional Euclidean space without introducing singularities or self-intersections. To say that a surface is two-dimensional means that, about each point, there is a coordinate patch on which a two-dimensional coordinate system is defined. For example, the surface of the Earth resembles a two-dimensional sphere, and latitude and longitude provide two-dimensional coordinates on it. The concept of surface finds application in physics, engineering, computer graphics, and many other disciplines, primarily in representing the surfaces of physical objects. For example, in analyzing the aerodynamic properties of an airplane, the central consideration is the flow of air along its surface. Definitions and first examples. A surface is a topological space in which every point has an open neighborhood homeomorphic to some open subset of the Euclidean plane E2. Such a neighborhood, together with the corresponding homeomorphism, is known as a chart. It is through this chart that the neighborhood inherits the standard coordinates on the Euclidean plane. These coordinates are known as local coordinates, and these homeomorphisms lead us to describe surfaces as being locally Euclidean. In most writings on the subject, it is often assumed, explicitly or implicitly, that as a topological space a surface is also non-empty, second-countable, and Hausdorff. It is also often assumed that the surfaces under consideration are connected. The rest of this article will assume, unless specified otherwise, that a surface is non-empty, Hausdorff, second-countable, and connected. More generally, a surface with boundary is a Hausdorff topological space in which every point has an open neighborhood homeomorphic to some open subset of the closure of the upper half-plane H2 in C. These homeomorphisms are also known as charts. The boundary of the upper half-plane is the x-axis. A point on the surface mapped via a chart to the x-axis is termed a boundary point. The collection of such points is known as the boundary of the surface, which is necessarily a one-manifold, that is, the union of closed curves. On the other hand, a point mapped to above the x-axis is an interior point. The collection of interior points is the interior of the surface, which is always non-empty. The closed disk is a simple example of a surface with boundary. The boundary of the disk is a circle. The term surface used without qualification refers to surfaces without boundary. In particular, a surface with empty boundary is a surface in the usual sense. A surface with empty boundary which is compact is known as a closed surface. The two-dimensional sphere, the two-dimensional torus, and the real projective plane are examples of closed surfaces. The Mobius strip is a surface on which the distinction between clockwise and counterclockwise can be defined locally, but not globally. In general, a surface is said to be orientable if it does not contain a homeomorphic copy of the Mobius strip. Intuitively, it has two distinct sides. For example, the sphere and torus are orientable, while the real projective plane is not. In differential and algebraic geometry, extra structure is added upon the topology of the surface. This added structures can be a smoothness structure, a Riemannian metric, a complex structure, or an algebraic structure. Extrinsically defined surfaces and embeddings. Historically, surfaces were initially defined as subspaces of Euclidean spaces. Often, these surfaces were the locus of zeros of certain functions, usually polynomial functions. Such a definition considered the surface as part of a larger space, and as such was termed extrinsic. In the previous section, a surface is defined as a topological space with certain properties, namely Hausdorff and locally Euclidean. This topological space is not considered a subspace of another space. In this sense, the definition given above, which is the definition that mathematicians use at present, is intrinsic. A surface defined as intrinsic is not required to satisfy the added constraint of being a subspace of Euclidean space. It may seem possible for some surfaces defined intrinsically to not be surfaces in the extrinsic sense. However, the Whitney embedding theorem asserts every surface can in fact be embedded homeomorphically into Euclidean space, in fact into E4. The extrinsic and intrinsic approaches turn out to be equivalent. In fact, any compact surface that is either orientable or has a boundary can be embedded in E3. On the other hand, the real projective plane, which is compact, non-orientable and without boundary, cannot be embedded into E3. Steiner surfaces, including Boy's surface, the Riemann surface and the cross-cap, are models of the real projective plane in E3, but only the Boy surface is an immersed surface. All these models are singular at points where they intersect themselves. The Alexander Horn sphere is a well-known pathological embedding of the two-sphere into the three-sphere. The chosen embedding of a surface into another space is regarded as extrinsic information. It is not essential to the surface itself. For example, a torus can be embedded into E3 in the standard manner or in a knotted manner. The two embedded tori are homeomorphic, but not isotopic. They are topologically equivalent, but their embeddings are not. The image of a continuous, injective function from R2 to higher dimensional Rn is said to be a parametric surface. Such an image is so called because the x and y directions of the domain R2 are two variables that parametrize the image. A parametric surface need not be a topological surface. A surface of revolution can be viewed as a special kind of parametric surface. If f is a smooth function from R3 to R whose gradient is nowhere 0, then the locus of zeros of f does define a surface, known as an implicit surface. If the condition of non-vanishing gradient is dropped, then the zero locus may develop singularities. Construction from polygons. Each closed surface can be constructed from an oriented polygon with an even number of sides, called a fundamental polygon of the surface, by pairwise identification of its edges. For example, in each polygon below, attaching the sides with matching labels, so that the arrows point in the same direction, yields the indicated surface. Sphere, real projective plane, torus. Klein bottle. Any fundamental polygon can be written symbolically as follows. Begin at any vertex, and proceed around the perimeter of the polygon in either direction until returning to the starting vertex. During this traversal, record the label on each edge in order, with an exponent of -1 if the edge points opposite to the direction of traversal. The four models above, when traversed clockwise starting at the upper left, yield sphere, real projective plane, torus. Klein bottle. Note that the sphere and the projective plane can both be realized as quotients of the two gone, while the torus and Klein bottle require a foregone. The expression thus derived from a fundamental polygon of a surface turns out to be the sole relation in a presentation of the fundamental group of the surface with the polygon edge labels as generators. This is a consequence of the Seifert-Van Kampen theorem. Gluing edges of polygons is a special kind of quotient space process. The quotient concept can be applied in greater generality to produce new or alternative constructions of surfaces. For example, the real projective plane can be obtained as the quotient of the sphere by identifying all pairs of opposite points on the sphere. Another example of a quotient is the connected sum. Connected sums. The connected sum of two surfaces M and N, denoted M'(N), is obtained by removing a disk from each of them and gluing them along the boundary components that result. The boundary of a disk is a circle, so these boundary components are circles. The Euler characteristic of M'(N) is the sum of the Euler characteristics of the summands, -2. The sphere S is an identity element for the connected sum, meaning that S#M equals M. This is because deleting a disk from the sphere leaves a disk, which simply replaces the disk deleted from M upon gluing. Connected summation with the torus T is also described as attaching a handle to the other summand M. If M is orientable, then so is T#M. The connected sum is associative, so the connected sum of a finite collection of surfaces is well defined. The connected sum of two real projective planes, P#P, is the Klein bottle K. The connected sum of the real projective plane and the Klein bottle is homeomorphic to the connected sum of the real projective plane with the torus. In a formula, P#K equals P#T. Thus, the connected sum of three real projective planes is homeomorphic to the connected sum of the real projective plane with the torus. Any connected sum involving a real projective plane is non-orientable. Closed surfaces. A closed surface is a surface that is compact and without boundary. Examples are spaces like the sphere, the torus and the Klein bottle. Examples of non-closed surfaces are an open disk, which is a sphere with a puncture, a cylinder, which is a sphere with two punctures, and the Mobius strip. Classification of closed surfaces. The classification theorem of closed surfaces states that any connected closed surface is homeomorphic to some member of one of these three families. The sphere, the connected sum of G tori, 4. The connected sum of K real projective planes, 4. The surfaces in the first two families are orientable. It is convenient to combine the two families by regarding the sphere as the connected sum of 0 tori. The number G of tori involved is called the genus of the surface. The sphere and the torus have Euler characteristics 2 and 0, respectively, and in general the Euler characteristic of the connected sum of G tori is 2 minus 2 grams. The surfaces in the third family are non-orientable. The Euler characteristic of the real projective plane is 1, and in general the Euler characteristic of the connected sum of K of them is 2 minus K. It follows that a closed surface is determined, up to homeomorphism, by two pieces of information: its Euler characteristic, and whether it is orientable or not. In other words, Euler characteristic and orientability completely classify closed surfaces up to homeomorphism. Closed surfaces with multiple connected components are classified by the class of each of their connected components, and thus one generally assumes that the surface is connected. Minoid structure relating this classification to connected sums. The identity is the sphere, while the real projective plane and the torus generate this monoid, with a single relation P#P# equals P#T, which may also be written P#K equals P#T, since K equals P#P. This relation is sometimes known as Dijk's theorem after Walther von Dijk, who proved it in, and the triple cross surface P#P# is accordingly called Dijk's surface. Geometrically, connect sum with a torus adds a handle with both ends attached to the same side of the surface, while connect sum with a Klein bottle adds a handle with the two ends attached to opposite sides of an orientable surface, in the presence of a projective plane. The surface is not orientable, so there is no difference between attaching a torus and attaching a Klein bottle, which explains the relation. Surfaces with boundary. Compact surfaces, possibly with boundary, are simply closed surfaces with a finite number of holes. Thus, a connected compact surface is classified by the number of boundary components and the genus of the corresponding closed surface, equivalently, by the number of boundary components, the orientability, and Euler characteristic. The genus of a compact surface is defined as the genus of the corresponding closed surface. This classification follows almost immediately from the classification of closed surfaces. Removing an open disk from a closed surface yields a compact surface with a circle for boundary component, and removing K open disks yields a compact surface with K disjoint circles for boundary components. The precise locations of the holes are irrelevant. Because the homeomorphism group acts k-transitively on any connected manifold of dimension at least 2. Conversely, the boundary of a compact surface is a closed one-manifold, and is therefore the disjoint union of a finite number of circles. Filling these circles with disks yields a closed surface. Riemann surface is a closely related example to the classification of compact two-manifolds is the classification of compact Riemann surfaces, i.e., compact complex one-manifolds. Since every complex manifold is orientable, the connected sums of projective planes are not complex manifolds. Thus, compact Riemann surfaces are characterized topologically simply by their genus. The genus counts the number of holes in the manifold. The sphere has genus 0, the one-hole torus genus 1, etc. Non-compact surfaces are more difficult to classify. As a simple example, a non-compact surface can be obtained by puncturing a closed manifold. On the other hand, any open subset of a compact surface is itself a non-compact surface. Consider, for example, the complement of a Cantor set in the sphere, otherwise known as the Cantor tree surface. However, not every non-compact surface is a subset of a compact surface. Two canonical counterexamples are the Jacob's ladder and the Loch Ness monster, which are non-compact surfaces with infinite genus. A non-compact surface M has a non-empty space of Nz, which informally speaking describes the ways that the surface goes off to infinity. The space E is always topologically equivalent to a closed subspace of the Cantor set. M may have a finite or countably infinite number nh of handles, as well as a finite or countably infinite number np of projective planes. If both nh and np are finite, then these two numbers, and the topological type of space of n's, classify the surface M up to topological equivalence. If either or both of nh and np is infinite, then the topological type of M depends not only on these two numbers but also on how the infinite one approach the space of n's. In general, th topological type of M is determined by the four subspaces of E that are limit points of infinitely many handles and infinitely many projective planes. Limit points of only handles, limit points of only projective planes, and limit points of neither. Surfaces that are not even second countable. There exist topological surfaces having no countable base for their topology. Perhaps the simplest example is the Cartesian product of the long line with the space of real numbers. Another surface having no countable base for its topology, but not requiring the axiom of choice to prove its existence, is the proof of manifold, which can be described by simple equations that show it to be a real analytic surface. The proof of manifold may be thought of as the upper half plane together with one additional tongue, Tx, hanging down from it directly below the point, for each real x. In 1925, T. Barrado proved the theorem that non-compact Riemann surfaces are necessarily second countable. By contrast, the existence of the proof of surface shows that there exist two-dimensional complex manifolds with no countable base. Proof. The classification of closed surfaces has been known since the 1860s, and today a number of proofs exist. Topological and combinatorial proofs in general rely on the difficult result that every compact two-manifold is homeomorphic to a simplicial complex, which is of interest in its own right. The most common proof of the classification is, which brings every triangulated surface to a standard form. A simplified proof, which avoids a standard form, was discovered by John H. Conway circa 1992, which he called the zero irrelevancy proof, or zip proof, and is presented in a geometric proof, which yields a stronger geometric result, is the uniformization theorem. This was originally proven only for Riemann surfaces in the 1880s and 1900s by Felix Klein, Paul Kober, and Henry Poincaré.